Welcome back to this fourth video on programming in C. Today I will be going over two new data types. We have float and double, and then we will be looking at how things are stored in memory, and then I'll be talking a little bit about binary. So let's go. Let's keep going where we left off last time. So this is kind of where we left off last time, with the exception of I've fixed that little mistake that I did in the last video. Now it says return 0, not return 1. So at the top here, at the beginning, we declare a couple of variables. They are of different data types. The first one is of the data type integer, which means that it holds a whole number, in this case the number 28, and it doesn't have any decimal point. And then we print those to the screen, and if we rerun this program, we can see that that's what it does. Okay, so let's introduce a new data type called float. Oops. Float. And unlike integer, floats can hold decimal point. They can have a decimal point. Correction, they must have a decimal point. They always have a decimal point. So if I want to write, for example, the temperature in Celsius, temp C here, that's the name of my variable, my floating point variable, and I give it the value 25.2. There we go. So now I've declared a floating point variable. And let's print that to the screen as well. Let's see what that looks like. There. Now let's run it and compile it. Or sorry, compile it and run it. Okay, so we see that it's printing. It is 25.20001 degrees Celsius. Oh, I have a little typo in here. And that 0001 has to do with how, when we're printing a floating point number, is actually converted to a different data type. And because of how arithmetic works on the floating point number data type, you sometimes get small inconsistencies like this. Errors. Floating point arithmetic errors, and they are very common, and you should know about them, and we'll learn more about them, but yeah, for now, just know that computers aren't always the best at handling arithmetic for floating point numbers. Okay, so we have the type float. We know that it can hold a decimal point, so that's good. And then we have another one. It's called double. And let's have that hold the temperature in Fahrenheit, right? And just like the floating point number, a double can also hold a decimal point. It can have a decimal point. Cool. All right, so let's do the same for this one. Let's print it. Degrees Fahrenheit. No. I think that's how you spell it. Fahrenheit outside, and that's going to be printing the variable F. Cool. Okay, let's... Oh, I did something wrong. What did I do wrong? Test, line 14. Each undeclared identifier is reported only once because we misspelled the variable name up here. There. Okay, works. What have I done wrong here? It's good to see. Let you see that I make mistakes as well. Okay. So you see there was no rounding error on this double variable. That is because when you're printing a floating point number, the floating point number is first converted to a double and then printed. If it is a double, it's already a double. It doesn't need to be converted. So yeah, so those are the two new data types. And let's look a little bit deeper into what makes them different from the other data types here and how they are stored in memory. Okay. So this is not the whiteboard solution that I was using earlier. I've switched to a different drawing software, so I hope you like it. It has pretty colors. So if we look at the example that we just did, we had a floating point number, float, and we named it temp c equals 25.2, and then a little semicolon here. And then, okay, so how does this get handled in memory? How does this get stored? So let's pick a different color here. Different color. So for simplicity's sake, let's just write memory here, and let that be like a big black, or in this case, blue box. Now this value here needs to be stored in memory somewhere. So let's just say that it's stored down here, and it's just put down there. For the computer to know where in the memory it has been saved, it needs to give it an address. So let's use some fancy colors again. Here we have its value, and that value is 25.2, and its address is some hexadecimal number, say 7FF ... So just as an example, this is not arbitrary numbers, but any variable that you store in memory needs to have an address so that your program can keep track of where that is stored in memory. So in other words, when we declare a variable like tempc, we say allocate some space in memory that is big enough to store a floating point number. Then store the value 25.2 in that space. This space has an address in memory, and let the name tempc be an alias that points to that address. To see the address that tempc is pointing to, we can actually do this in code. Let's see. Okay, so how do we do this? We need to add another printf statement, and right here. There. Okay, so let's just run it. Compile and run it and see what it does. Okay, so it says the address in memory where the value of tempc is stored is 0061FF00. Why is there letters in this address, you might ask? Was because this address is printed here in hexadecimal form. So that's just how that looks. I won't go into hexadecimal, but that's the address where this value is stored. Yeah. And so you can see %p here. That stands for pointer. We will definitely be looking more at pointers. And then to be able to write the address of that variable, we have to add this and symbol right in front of it. This is C, just the way you do this in C. Okay, so now we can actually see the address in memory that this variable has been stored at. So there's one more piece to this puzzle of understanding what the differences are between these data types. And that is, we have to understand a little bit of binary. Like I mentioned before, your computer only really understands zeros and ones. So the variables that we create needs to be stored in memory as zeros and ones, as binary. So let's write some examples here. How can we write numbers as binary? So say, for example, that we have decimal over here, and we have binary over here, right? Let's change the color again, just for funsies. And so the decimal number. So you and I, we usually, when we count in decimal. Deca is in like 10, because there are 10 different numbers that you can use to represent a single digit. So that is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's 10 different digits, including 0. So, but in binary, you only have 2 different numbers to represent a single digit, which is 0 and 1. That's it. So if we start with the number 0 here in decimal, that is 0 in binary. So far, so good. 1 is 1. 2 is 10. What? Why 10? Well, realize that with decimal numbers, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And when you get to 9 and you want to add one more, what do? You get 10. So you kind of roll over, and this ones place becomes 0 again, and the tenths place becomes 1. Well, the same happens with binary, because now we've run out of the possibilities that we have on the first digit here, and so we roll over and we get a 1 in that place and a 0 in here. And so if we keep going, 3 is 1, 1, because 10 plus 1, so that's what that looks like. 4 is 100 in binary. And so it keeps going. 5 equals 101, 6 equals 110, 7 equals 11, and 8 equals 1000. That's a little bit of binary. Just as kind of like a side note here, as an example, say for example, the decimal number 100 is the binary number 100111010. That's what 100 looks like in binary. Then we should understand what the difference is between a bit and a byte. So you can say, if I write here, 1 bit is 1 digit of zeros or ones. And a byte, so 1 byte with a capital B, byte, and a Y there, is 8 bits, or 8 digits of zeros and ones. So in other words, which color should we use this one? 1 B, capital B, byte, is 8 bits, lowercase b. So how much space in memory do these data types take up? Let's write a bit of code here. There. So what I'm doing here, I'm using this size of function, which, what does that do? It actually takes that data type and then returns the number of bytes that should take up in memory. So if I run this, you can see that the float data type takes up 4 bytes in memory, and the double data type takes up 8 bytes in memory. I should write these with capital B here. 4 bytes in memory. Cool. So yeah, so 4 bytes, there's 8 bits per byte, so 4 times 8 is 32 bits. So the floating point data type takes up 32 zeros and ones in memory to represent that value. Whereas the double takes up double that amount of space and takes up 64 zeros and ones in memory. Just by the way, when I say that a variable is stored in memory, I mean that it gets stored in your computer's RAM. RAM stands for Random Access Memory. And yeah, here's an example. This is an 8 gigabyte stick of RAM, which means that it has 8 million bytes of capacity. Like you can store 8 million bytes of zeros and ones in here. That's 8 million times 8 zeros and ones. So it's just an insane amount of volume, and you usually have like 1 or even more of these in your computer, typically 2 to 4. So yeah, just modern day computers can store so much data. But so here is the point that I wanted to make. In memory, a floating point number takes up less space than a double does. All right. So, what have we gone over today? We have looked at 2 new data types, float and double. We've seen them here. We have looked at how these variables get stored in memory, and then we also learned a little bit about binary, and we can see how big our data types are here. Okay.